Module 5 Mastery Assignment by Leslie Oy. Topic 1. Average value of a function. The average value of a function is really just the average y value of a function. In other words, it is the average height of a function. Average, remember, is a measure of the center in a dataset, which is the mean. Here are some other helpful key terms you should know. Definite integral, which is the net signed area bound by a function in the x-axis, and FTC, or Fundamental Theorem of Calculus, which is a rule that links together a function and its derivative, or a function and its antiderivative. The average value of a function f of x on the interval from a to b is defined by the following formula. 1 over b minus a, which is the upper limit minus the lower limit, is multiplied by the definite integral from a to b of f of x dx. And you'll notice that the units of f of x and its average value will be the same. Average value can also be graphically represented. A horizontal line on a graph can be used to represent the average y value of a function, and the distance from the x-axis to that horizontal line is the actual average value of the function. Here I've shown an example, and the brown line would be used to represent the average y value of the function, and the distance, which is shown with the red line, is the distance from the x-axis to the horizontal line, which is the actual average value of the function. And when you find the net signed area bound by the function and this horizontal line, it's actually going to end up being 0. We can also connect the average value of a function to the Fundamental Theorem of Calculus Part 1. Remember first that the Fundamental Theorem of Calculus states that f of b minus f of a equals the definite integral from a to b of f of x dx, where the first derivative of the antiderivative equals f of x. So, when we divide both sides by b minus a, as shown, and then we can rewrite it to f of b minus f of a all over b minus a equals 1 over b minus a times the definite integral from a to b of f of x dx. From this, we can gain that the left side of the equation represents the average rate of the change of the antiderivative on the interval from a to b, while on the right side, it can be used to represent the average value of the function f of x on the closed interval from a to b. Both expressions represent essentially the same thing because they are exactly equal to each other on the same interval. Now that we know these things, let's look at an example. Find the average value of the following function on the given interval f of x equals 3x squared over the closed interval from 0 to 5. First, we're going to find the antiderivative, and in this case, it's going to be equal to x cubed. Now, we can evaluate it from 0 to 5. So we plug in 5, and we plug in 0, and we're going to get 5 cubed minus 0 cubed, and when we solve this, we're going to get 125. And then we're going to divide it by 5 since that's the length of our given interval, and we're going to get 25. So essentially, our setup would be 1 over 5 minus 0, which is our upper limit minus our lower limit of integration, times the definite integral from 0 to 5 of 3x squared dx. In this example, I integrated the function by hand, but this can also be plugged into the calculator. Topic 2. Area between two curves. The area between two curves is the measurement of the area of a region bounded by two functions. However, a common misconception is when first introduced to definite integrals. The concept is linked to being a representation of the area under the curve. However, the area shaded in the graph is not always the same as its integral. An example that illustrates this is the graph of sine of x over the interval from 0 to 2 pi. While it has an integral of 0, its area over the same interval is 4. If f of x and g of x are piecewise continuous functions on the closed interval from a to b, and f of x is greater than or equal to g of x on the closed interval from a to b, then the area between the curves is given by the following. Area equals the limit as n approaches infinity of the summation as k goes from 1 to n of f of x sub k minus g of x sub k, all multiplied by delta x. This is also known as the Riemann sum approximations, as the number of rectangles increases to infinity, and all of this is equal to the definite integral from a to b of f of x minus g of x dx. It is important to note that when asked to find the area enclosed by intersecting curves, the intersection points are the limits of integration. Intersection points are where functions are equal to each other. Now that we know these things, let's look at an example. Find the area of the region enclosed by y equals 2 minus x squared and the line y equals negative x. Here I've graphed it for us, and I've shaded the region which we are trying to find. When we graph it, notice the upper curve is the parabola and the lower curve is the line. So now, we need to find the intersection points for limits of integration. First, we're going to set the equations equal to each other, so 2 minus x squared equals negative x, and then we're going to get it all to one side, so 0 equals x squared minus x minus 2. And then we factor it, so x minus 2 times x plus 1. So our solutions will be x equals 2 and x equals negative 1. Now that we have our limits, we can integrate it. So area equals the definite integral from negative 1 to 2 of 2 minus x squared minus negative x dx, which simplifies to the definite integral from negative 1 to 2 of 2 minus x squared plus x dx. And then we'll find the antiderivative, which will be 2x minus 1/3 x cubed plus 1/2 x squared, and then we're going to evaluate this from negative 1 to 2. So f of 2 minus f of negative 1, when we plug in both of those values, we're going to get 10/3 minus negative 7/6, which simplifies to 10/3 plus 7/6. And then we are going to change the 10/3 into sixths, which will be 20/6 plus 7/6, and that's going to give us 27/6. And that finally simplifies all to 9/2, which will be our area between 2 minus x squared and negative x.